Here you see a BCD to 7-segment decoder driver IC. These ICs are found in multimeters, counters, and other test equipment, commercial electronic scales, or wherever a numerical readout is required. Notice that the IC pin configuration is the same for the DM7446A, DM7447A, and the DM7448. The primary difference between these ICs is in their voltage and current requirements. Their operation, however, will remain the same. To better understand how the decoder driver IC works, we will examine this simple circuit. At this point, you should already be familiar with the operation of the counter circuit and the display device. As you can see, this counter circuit outputs a BCD code. When the counter circuit is at 0 counts, the BCD code of 0000 is fed into the inputs of the decoder driver IC. The decoder portion of the IC decodes the BCD input and causes the driver portion of the IC to output a high into outputs A, B, C, D, E, and F. This results in a 0 being displayed on the 7-segment display. When the counter IC increases by 1, the BCD code of 0001 is directed into the BCD inputs of the decoder driver. The decoder driver decodes the BCD input and causes outputs B and C to turn on. This results in the 7-segment display showing a numeral 1. As the counter IC further increases by another count, it outputs a BCD code of 0010 into the inputs of the decoder driver. The decoder driver decodes this input and produces a high output on pins A, B, D, F, and G. This results in the numeral 2 being displayed. As the counter IC increases by one more count, it outputs a BCD code of 0011, which is then fed into the inputs of the decoder driver device. The decoder driver decodes the BCD code and causes outputs A, B, C, D, and G to turn on. This results in the numeral 3 being displayed. When the counter IC increases by yet another count, it produces a BCD coded output of 0100. This BCD code is then decoded by the decoder driver IC, which causes B, C, E, and G to go high. When segments B, C, E, and G are illuminated, the numeral 4 will become displayed. By increasing the counter by another count, it produces a BCD output of 0101. This output is then directed into the BCD inputs of the decoder driver IC, where it is decoded and sent to the 7-segment display. The decoder driver device will cause outputs A, C, D, E, and G to energize, which causes the numeral 5 to be displayed. When the counter again increases by a count, it produces a BCD code of 0110. This BCD code is then fed into the decoder driver device. The decoder driver decodes the BCD code and causes outputs C, D, E, F, and G to go high, which results in the numeral 6 being displayed. As the counter IC once again is increased by 1, a BCD code of 0111 is computed into the decoder driver device. The decoder driver decodes the BCD code and outputs a high on A, B, and C. This results in the numeral 7 being displayed. By increasing the counter IC by yet another count, it causes the counter to output a BCD code of 1000. This output is then fed into the BCD inputs of the decoder driver IC, which causes the decoder driver to turn on outputs A, B, C, D, E, F, and G, and as a result, the numeral 8 is displayed. And by increasing the counter chip by one more count, it causes the counter IC to produce a BCD coded output of 1001. The 1001 is then directed into the BCD inputs of the decoder driver device, where it is decoded and fed into the 7-segment display. The decoder driver will turn on outputs A, B, C, E, and G. This causes the numeral 9 to become displayed. As you can see, by controlling the counter integrated circuit and using the decoder driver IC to decode the output from the counter and drive the 7-segment display, a simple circuit can be built which will count from 0 to 9. A circuit capable of counting higher than 9 may be designed by cascading a series of counter decoder driver ICs to any given length desired. In this simple circuit shown, the 50 kHz oscillator is fed into a divide by 50,000 counter. The 1-second pulses are then fed into a divide by 10 counter. The divide by 10 counter outputs a BCD code into a decoder driver IC, which is also used to drive a 7-segment display. When the first divide by 10 counter reaches 9, it resets back to 0 and outputs a pulse into the next divide by 10 counter. This pulse activates the second counter circuit and causes it to produce BCD-coded outputs into its decoder driver circuit. The decoder driver IC causes the 7-segment display to show the divided down pulses in a numerical form. By simply adding more counter decoder driver 7-segment display devices, this circuit can be made to count to any desired length. It was mentioned earlier that a character generator was required to operate the dot matrix display. The character generator selects the specific diodes to be turned on by a method referred to as scanning. The character generator is generally a ROM device, which is programmed to output 64 characters from a 6-bit address input. ROM stands for read-only memory. The address inputs are labeled A1, A2, A3, A4, A5, and A6. A character code is fed into the address inputs, at which point the character generator is programmed to activate the designated column drivers and the row address at one time. As the character generator scans each row, it places new information on the column driver lines, which change from scan to scan. By changing the data supplied from the column driver outputs with each scan, various character combinations can be achieved. To better understand how the character generator works, we will examine this simple circuit. Notice that it consists of a character generator with the 6 character code address lines, as well as outputs for the row addresses and column addresses. Also shown is a 5x7 dot matrix display. We will begin by placing the code for the uppercase letter S on the character code address input lines. Notice that the character code for the letter S is 010011. This code is placed at code inputs A1 to A6. The program contained within the character generator will decode this input data and cause the character generator to select row 1 of the dot matrix display. At the same time, the LEDs in columns 2, 3, and 4 will become activated and turn on. Shortly after row 1 is scanned, row 2 will be scanned, and the data from the column outputs will change and turn on the LEDs in columns 1 and 5. Next, row 3 will be scanned, and the output going into column 2 of the dot matrix display is energized. This causes the diode at column 2, row 3 to turn on. Then the character generator scans row 4. As row 4 is scanned, the character generator will output a high into column 3, thereby turning on this LED. The character generator then scans row 5 and activates the column output for column C4. This allows the LED at C4 row 5 to turn on. Next, the character generator scans row 6 of the dot matrix display. It also outputs a high into column 1 and column 5 of the display. This forces both LEDs to illuminate. Then the character generator scans row 7 of the dot matrix display and at the same time activates the outputs for columns C2, C3, and C4. The character generator will continue to sequence for as long as the character must be displayed. The sequence, however, is so fast that the eye sees the character as being illuminated all at one time. Here you see the SN7441A, which is a BCD to decimal decoder Nixie tube driver shown with a Nixie tube. The BCD numbers to be decoded is applied at the 4 inputs labeled A, B, C, and D. This decoder driver operates much like the 7-segment device previously discussed. except that the SN7441A will only activate one output at a time. The outputs are designed to drive gas-filled Nixie display tubes. The output voltage of this device will typically be 70 volts with a supply current of 36 milliamps. When in operation, the correct filaments are energized, causing the neon gas around the filament to glow.